Welcome to second session of the lecture. We are going to talk about MRE phase shift keying. MRE phase shift keying. Which is the digital version of phase modulation. By name, it suggests that the message signals information has to be embedded in the phase of the carrier, right? So you are going to witness some changes in the carrier's phase, some addition in the carrier's phase in these analytical expressions. We again consider the mth modulated signal, which is expressed in exponential form as real under root 2 es divided by ts. This is the carrier's amplitude, again expressed in terms of the symbol's energy and the symbol time ts. E raised to the power j 2 pi by m small m minus 1. I'll explain what is this term, and the carrier term here, e raised to the power j 2 pi fct, where small m varies from 1 till capital M. Now if you combine these two exponentials, you will see this thing will contribute in the phase of the carrier, right? For example, if I write the phase inside this exponential, so it will be e raised to the power j 2 pi fct plus 2 pi by, or you may just remove the brackets, plus j 2 pi by m small m minus 1, right? Now this term basically is the phase phi m. The phase is controlled by the index small m, right? So if you vary small m from 1 till capital M, you are going to get different phases as a result, and all these phases are going to get added onto the carrier term's phase, right? So we assume the carrier has, say, 0 phase initially, but as the message signal changes, this small m will vary, right? Since the small m depends on the combination of the bits, right? So as the message signal varies, the small m is going to vary, and you will end up computing a unique value of the phase out of it, right? And that phase value is added onto the carrier's phase. So in short, we are embedding the message signal's information into the phase of the carrier term, right? So we express it in general expression, we express it like that. And the nth signal, modulated signal, is expressed in terms of the index m and the carrier frequency like this. Let's remove the real operator. We end up getting 2es divided by ts cos of 2 pi fct. And by the way, our signal was rectangular in shape. The pulses that we had are rectangular. We use rectangular pulse shaping in short. So under that assumption, we end up getting this expression plus 2 pi by m minus 1. If you apply the trigonometric identity here, cosine trigonometric identity, we can expand this in terms of two cosines, two terms basically. Under root 2 ES divided by TS cos of small m minus 1 minus under root 2 ES divided by TS sine of 2 pi FCT sine of 2 pi by capital M small m minus 1, right? Right, so now if I ask you to assume a scenario in which you have again capital 4 signals, assume m is equivalent to 4, right? You substitute small m equivalent to 1 till equivalent to 4 in this expression, generalized expression, you will end up getting 4 different signals, right? And if I ask you to compute the basis function representation of those 4 symbols, right? So as a result, the basis functions will come out to be, again from GSO process, assuming you are able to do the GSO process and you are able to apply the concepts of GSO process, the methods onto this problem, the basis functions for M array PSK will come out to be phi 1 of t, which is equivalent to 2 over TS, 2 over under TS cos 2 pi FCT, and phi 2 of t, which is 2 over under TS sine 2 pi FCT. Interestingly, you will always end up getting the two basis functions, phi 1 of t and phi 2 of t, for any value of capital M, right? Of course, other than 2, if you substitute 2 here, if you substitute capital M equivalent to 2, you will only get one basis function, which is the special case, which becomes equivalent to amplitude shift keying as we did earlier. But for larger values of capital M, you will always end up getting two basis functions and no more, right? So in short, we can express our modulated term as m of t using the same basis functions calculated out of the GSO process. These two are calculated out of the GSO process. Right? And I guess I gave you one assignment in which you are asked to compute the basis functions of the two sinusoids, right? And you end up getting the two basis functions like this. So let's express Sm of t in terms of the basis functions and then expand the 4 signals and see how the expressions look like. Sm of t will be, let's first write down the generalized expression, then substitute capital M equivalent to 4. Sm of t will be under root E as cos of 2 pi by M small m minus 1 phi 1 of t, where phi 1 of t was that basis function substituted there, right? Here you can see the representations. If you substitute phi 1 of t here, in other words, express this whole equation in terms of phi 1, you will see phi 1 of t replacing some portion of this term there, which is written here, and the other portion is written as it is. And similarly here, this term will be replaced with phi 2 of t. Excuse me. So the remaining portion will become minus under root es sine of 2 pi by m small m minus 1 phi 2 of t. Right, now this is your generalized expression for M array PSK. M array PSK. Phase shift keying. M array phase shift keying generalized expression where small m varies from 1 till capital M. And now let's expand for capital M equivalent to 4 and see how the phases come out to be. Since we are calling it phase shift keying, then you need to see how the different unique phases are being added onto the carrier signal's frequency, right? So let's see the calculation behind the different phases and of course the expressions. So if you substitute capital M equivalent to 4, you are going to get 4 different signals, right? S1 of t will be under root es cos of 2 pi by 4. Small m is substituted as 1, which is 1 minus 1 phi 1 of t minus phi 2 of t. So if you solve it further, this will be 0, since sine of 0 is equivalent to 0 and cos of 0 is equivalent to 1, right? So S1 of t will be under root es phi 1 of t, right? If I ask you the value of the phase, this term, the bracket term, basically represents the phase, right? Where is it? 2 pi by m times m minus 1, right? So the phase comes out to be for index m equivalent to 1, small m equivalent to 1, which is 0. The phase comes out to be 0 degree, right? So S1 of t is equivalent to under root es phi 1 of t. You will understand the meaning of this 0 degree shortly. Once we express our signals onto the constellation diagram, you would be able to see the different phases. So the first phase comes out to be 0 degree and the modulated term is expressed in terms of the basis function like this. Right? The other term is 0 times phi 2 of t. Effectively you just have this term, meaningful portion, right? 0 times phi 2 of t will be 0. When small index m is equivalent to 2, your modulated signal becomes S2 of t and it will be equivalent to under root es cos of 2 pi by 4 small 2 minus 1, right? Small m is equivalent to 2 minus 1 phi 1 of t minus under root es sine 2 pi by capital M equivalent to 4 and small m equivalent to 2 again phi 2 of t, right? Now what's the phase? 2 minus 1 is 1. 2 pi by 4 is the phase, or in other words, pi by 2 is the phase for this particular scenario, right? So how do you write it? Cos of 90 is what? 0. This term will be 0. What about this? Sine of 90 is 1. So this term will be 0. And this term will give you minus under root es phi 2 of t as a result. So S2 of t is there, minus under root es phi 2 of t with the phase of 90 degree. The phase is 90 degree. Phase in the carrier term is 90 degree. How about m equivalent to 3 and m equivalent to 4? S3 of t likewise will become, if I solve it directly, compute the answer, you can check later, it will be minus under root es times phi 1 of t. And S4 of t will be under root e as phi 2 of t, right? Now let's plot it onto the constellation diagram. Since we have two basis functions, we have two axes. One axis belongs to phi 1, the other one belongs to phi 2. We assume all the signals are equally likely and equal energy. The ES is same for all of the signals, right? So signal S1, symbol S1 is nothing but under root ES times phi 1, okay, which we computed over there. Symbol S1 is under root ES times phi 1. That is, it is plotted on to the phi 1 axis, right? And its norm is equivalent to under root ES, right? Symbol S2 is minus under root ES phi 2, means this is the phi 2 axis, right? And this is the negative portion of it below this point. And this value there is symbol 2, which is minus under root ES. Symbol 3 is minus under root ES along the phi 1 axis, that is there. This is the symbol 3, minus under root ES. And symbol 4 is positive under root ES along the phi 2 basis function, that is here, under root ES, and which is symbol 4. So all these symbols are plotted onto the same constellation diagram, and you can see there they have different phases, right? This one was having 0 degree phase, this one was having 90 degree phase, another 90 degree added onto it, and then 270 degree, right? So index small m controls the phases values. If you draw the table like we did for pulse amplitude modulation, suppose we had 4 symbols, we are going to have 4 possible combinations of the bits, right? And each combination of the bit belongs to one particular phase. It translates itself into one particular phase, right? You call it phase. Here is the index m. One, 2, 3, and 4. We have 4 symbols at hand. So the index will vary from 1 till 4, and the phase will be computed as per the rule that we have defined here. That's the phase, 2 pi by m times small m minus 1. So we are going to put this expression in this column. Write it as phase 2 pi by m small m minus 1, right? And if you compute it for capital M, let capital M is equivalent to 4, you end up getting these 4 terms, the pairs, mid pairs. You compute the phase, you will get 0 degree here. When you substitute 1 there, you get 0 degree phase, which is phi 1. Phi 2 is 90 degree, basically pi by 2 here, and about phi 3. If you substitute 3 here, 3 minus 1 is 2, which is 4. 4 pi by 4, it is pi, right? And phi 4 is nothing but substituting 4 here. 4 minus 1, 3. 6 pi by 4. In other words, 3 pi by 2, which is 270 degree, right? So we end up getting these 4 unique phases for 4 different message signal combinations, right? In our case, if you assume capital M equivalent to 8, right, you will be using 3-bit combinations for your message signal, and you would have 8 such rows, 8 different message signals, unique message signals, along with 8 different phases, right? And you might have 4 more points populated onto this constellation diagram representing different unique phases, right? Now again, we can see that we have translated our problem onto the constellation diagram very easily, right? And from there, and this point onwards, all we are required to find out the average probability of error in terms of the function. And in the last lecture, we have seen an example in which we had 2 basis functions and 4 different signals, right? And we computed the probability of error in a very nice form, simplified Q function form there, right? And it turns out that the same answer that we computed last time will be valid here as well, since we have a slightly different constellation. It's tilted one. In the last example, we had the constellation in which we had the points here in the quadrants, right? The 4 points were there in the quadrants, right? But the phase difference between them was similar. And here in this particular example, we have the points here along the axis, right? And again, the phase difference between them is the same. So it turns out that the probability of error for this constellation, the black one, will be the same as the probability of error for this constellation, the green one, right? And that you can verify, because it's nothing but the tilted version of the same constellation. If you tilt it by 45 degree, the green constellation by 45 degree, it will end up becoming the black one, right? So this tilt will not vary the probability of error analysis. The analysis will hold true for this constellation as well. So we have computed the probability of error already for this particular type. In short, I'm saying that we have already computed the probability of error for M array QPSK. QPSK, why? Because we have 4 different signals, we call it QPSK. Instead of writing 4 PSK, we call it QPSK, well-known notation for this particular scenario. We call it QPSK, quadrature phase shift keying, right? We have quadrature axis, this axis, normally referred as I axis or in phase axis, and this axis is referred as Q axis or out of phase axis, quadrature axis, right? So we call it, in short, quadrature phase shift keying, right? And suppose we have more values, suppose M equivalent to 8, then we have more signal points, right? Till 8. More points in the constellation diagram, right? And you will find out that all these points, if you compute the norms of these signals, it will turn out that all these values will be the same. That is, the difference between the signal point with reference to the origin will remain the same. In other words, if you populate more signals, they will be placed along this circular boundary, right? If you compare this scenario with M-array ASK as we did earlier, when you have more signals, they will be placed along the single axis, the phi 1 axis, or say x axis. And as you place more and more signals, the signals will be spaced apart from each other, right? But here you see the energy with reference to the origin doesn't change as you populate more and more signals. However, the difference between the signals will reduce as you populate more signals onto the constellation diagram. And this is something which will increase your probability of error, since you are getting more decision regions as you populate more and more signals here in this constellation diagram. And it's very likely that the received signal may fall in the other decision regions, and hence will contribute towards the probability of error because of the noise. So if you have a very bad channel, when the noise strength is very high compared to the signal strength, you may not go for higher modulation schemes in which capital M is very high. You would like to reduce the value of capital M. In other words, you would like to go for lower end modulation schemes, so that the likelihood of one signal, the received signal, falling onto the other signal's decision region is made less. Okay. Right, so now let's compute a few other parameters like we did for ASK. We would like to compute the generalized formula that calculates the difference between any two neighbor signal points. Okay. Right. For the sake of simplicity, assume we are having the same example in which capital M is equivalent to 4, and we choose 2 points out of these 4 points and write down those 2 points here from the constellation diagram. If we see it, the first point is written as under root E cos of 2 pi by M 1, comma, under root E sine of 2 pi by M 1. Let me draw the constellation here so that you don't get confused. this was basically m minus 1, right? Assume m is chosen as the 2 points are m equivalent to 2 and m equivalent to 4. M equivalent to 3, sorry. We are talking about these 2 points, right? So if you substitute m equivalent to 2 and 3 there, you will end up getting the 2 points as under root e cos 2 pi by m 1 and the other 2 points as this, right? This is true for m is equivalent to 2 and this is true for m is equivalent to 3. Right? So we are getting the 2 points there. We would like to calculate the Euclidean distance between the 2 points. So these are the 2 points and the x component, the y component of it, similarly the x component of the second point and the x component of the y component of the second point, right? So we have 2 components, x1 and y components, so we end up getting the 2 constellation points respectively. Now let's compute the Euclidean distance between these 2 points in general. So using the same formula as we did for the ASK, we would like to subtract the contributions and take the squares and under root to compute the overall distance between the 2 neighbors. So D12 will be equivalent to, in other words, D23 will be equivalent to, since we are computing the distance between the signal point 2 and signal point 3. So D23, or in other words, the distance between D2 and D3 will be equivalent to, or you may consider the distance between D1 and D2 is the same as the distance between D2 and D3. So in short, this is equivalent to D minimum, which is equivalent to S11 minus S21 square what are these S11 and S21? These are these values, right? This one corresponds to the basis function, the small one, the basis function index, and this, the first one, and this 2 corresponds to the contribution of the signal class. This is the contribution of the signal class 1 onto the basis function 1, and this is the contribution of signal class 2 onto the basis function 1, right? So you subtract these contributions and take the square, and similarly, likewise, you go for the other contributions. This is a contribution from signal 1 onto the basis function 2, and this is a contribution of signal 2 onto the basis function 2, right? You subtract the contributions there as well. So if you substitute the values, you end up getting a very lengthy expression. under root E cos 2 pi by m minus under root E cos 2 pi by m times 2 whole square. Right? So I've substituted these two values. This one for S11 here, and this one for S21 there. Take it. Plus under root E S sine 2 pi by m minus under root ES sine 2 pi by m times 2, right? All square. That is, this term is nothing but S12 substituted there, and this term is S22 substituted here, right? Now if you expand this and solve it, expand the squares and simplify it, you will get this expression under root of, I'm writing the simplified expression, under root of 2ES 1 minus cos of 2 pi by m, bracket close. This is your D minimum, that is the Euclidean distance, the minimum Euclidean distance in this constellation, which is nothing but the distance between the two neighbors, right? If you compute the distance between these two, this will be equivalent to D minimum. As per this formula, it will be equivalent to, if you substitute the value of 4 here, this is cos of 2 pi by 4, you will end up getting some value for the D minimum. Right? If you solve it, it will be under root of 2ES 1 minus cos of 2 pi by 4. Which is equivalent to under root of 2ES. Why? Because cos of 90 is 0, right? This is cos of pi by 2. Cos of 90 is 0. So 1 minus 0 is 1, and you will end up getting under root of 2ES. So this distance is under root of 2ES, which is same for all these points. Under root 2ES, under root 2ES, and finally this distance is under root 2ES. Remember, this is the distance between the two neighbors, right? This is under root 2ES, the minimum distance between the neighbors. As you increase the value of m, capital M, this distance will reduce. The distance between the two neighbors will reduce because, like I said earlier, you are going to include more points there on the same circle, right? So the minimum distance will reduce, right? In general, if I ask you to find out the distance between any two signal points, assume we have more signal points, right? So in general, if I ask you to find out the distance between any two signal constellation points, let's call it DKM. The distance between the kth signal class and the mth signal class point on the constellation diagram, DKM, is equivalent to under root of, using the same analysis, all you have to do is to substitute K here, K class here against this one there, and M class there. Previously we have substituted signal class 1 and signal class 2, right? Now in general, if I ask to find out the distance between the kth signal class and the mth signal class, so you're going to substitute k here and m there, small m there, and do the same analysis, right? You will end up reducing the equation in this form: 2e 1 minus cos of 2 pi by m, capital M, m minus k magnitude, right? This doesn't even matter because the cos is an even function. Even if you have negative sign, it will be neutralized by the cosine function. So this is the generalized formula if you would like to compute the distance between any two signal points. If you substitute k and m with a difference of 1, this means you are computing the distance between the two neighbors, and that will give you, spit out the minimum distance between the two constellation points, which is equivalent to under root 2 ES. So if I compute in case of 8 signals, you may substitute 1 here and 5 there. You will be computing the distance between the signal class 1 and signal class 5. All you have to do is to substitute these values m and k, and you will end up finding the distance between those two constellation points in the diagram, right? All right, I'll stop here, and the next particular type of modulation is FSK, frequency shift keying, which we will talk about in the next lecture. We will see the FSK, and we would also like to compute the probability of error calculations for those signal classes in which capital M is greater than 4, say, for example, it's greater than 4. So for higher constellation sizes, we may not use this traditional method to compute the Q functions and probability of error. We may go for some approximations using some error bounds. We will talk about those error bounds in the next lecture. All right, if you have any question, you can use interactive session. Thank you.